From the terminal, starting a jet engine looks almost effortless. A switch is flipped, and within seconds, several tons of stationary precision machinery spins to thousands of revolutions per minute. Inside the nacelle, it is anything but. Airflow must exist before fuel is introduced. Ignition must arrive at precisely the right moment. The compressor must accelerate fast enough to sustain itself. And temperatures must stay within limits that protect components worth millions. If any part of that sequence goes wrong, the flight crew may have only seconds to stop the start before heat, unburned fuel, or a stalled core turns a routine procedure into something far more serious. There are three escalating reasons why. The CFM56-7B turbofan on a Boeing 737 operates on a continuous, closed aerodynamic cycle. When the engine is running, fuel burns in the combustion chamber, generating hot, expanding gas. This high-energy gas rushes backward through the turbine stages, spinning them at thousands of revolutions per minute. Because the turbine is connected directly to the front compressor by a central steel shaft, this rotation drives the compressor, drawing in and compressing fresh air to sustain the combustion. It is a highly efficient, self-sustaining loop of physical energy. But a stationary engine possesses none of this momentum. When the aircraft sits parked at the terminal gate, the core is completely cold and motionless. There is no airflow, no compression, and no turbine rotation to draw air into the combustor. If the flight crew simply introduced fuel and a spark into this static environment, the fuel would merely pool at the bottom of the combustor or burn in a localized, highly destructive fire. Without a pre-existing wall of high-velocity airflow to force the intense heat backward through the turbine, the engine cannot survive ignition, let alone generate the power needed to drive itself. Because of this, a stopped jet engine is physically incapable of starting itself. To bridge the gap between a dead machine and a self-sustaining turbine, the flight crew must initiate a sequence that borrows energy from an external source. This initial physical rotation must be supplied from outside, using high-pressure air from the auxiliary power unit in the tail, a ground air cart connected on the ramp, or a dedicated electric starter. This external system must force the heavy core machinery to rotate, creating the initial draft of air before the first drop of fuel can be safely introduced. The transfer of this external energy follows a highly specific physical path. It begins when high-pressure bleed air, sourced from the auxiliary power unit or a ground cart, reaches the starter air valve. This electrically controlled butterfly valve opens, directing the pressurized air into the air turbine starter. The starter turbine converts the kinetic energy of the pneumatic air into mechanical torque, which it sends directly into the accessory gearbox. From this gearbox, the torque passes through a transmission gearbox, an intermediate gearbox, and a radial drive shaft to begin spinning the high-pressure core spool, which contains the high-pressure compressor and its driving turbine. In the cockpit, pilots monitor this initial rotation through a single instrument parameter, N2. Defined as the rotational speed of the high-pressure core rotor, N2 is expressed as a percentage of its maximum design speed. For the reference CFM56 engine, 100% N2 represents approximately 14,400 revolutions per minute. At the beginning of the start sequence, this gauge sits at 0, and the starter must work against the immense inertia of the heavy steel core. It is a common assumption that the starter's job is to directly light the fire inside the engine. In reality, the starter serves a far more clinical purpose. It must generate aerodynamic flow. Before any spark or fuel can be introduced, the high-pressure compressor must spin fast enough to force a controlled, high-velocity column of air through the combustor and out through the turbine. The starter is not starting the fire, it is creating the physical environment that makes the fire survivable. This physical requirement establishes a rigid, unyielding sequence of events. First, starter power is applied. Second, the compressor begins spinning. Third, internal airflow develops. Fourth, the ignition system activates. Fifth, fuel enters the combustor. Sixth, combustion begins. Seventh, the turbine accelerates under its own power. Finally, the engine achieves self-sustaining operation, where it no longer requires the starter to keep running. Timing is the primary vulnerability of this transition. Each subsequent step is entirely dependent on the physical conditions established by the step before it. If fuel is admitted into the engine before the compressor has accelerated to roughly 25% N2, the air moving through the core will be too weak to control the flame. The compressor must be moving enough controlled air through the core to show or to act as an aerodynamic barrier, shielding the turbine components from the raw heat of the flame. Without this pre-existing mass of fast-moving air to carry the thermal energy away, the heat of combustion would simply pool inside the stationary machinery. For this reason, the machinery must be brought to life in a sequence where physical movement always precedes fire. Once the igniters spark and fuel enters the combustor, the engine enters its most thermally vulnerable state. To an observer, the first indication of ignition, known as light off, might feel like the moment of safety. In reality, it is where the thermal risk begins. At this stage, the engine is producing intense heat, while the airflow moving through the core is highly restricted, often less than 5% of its normal takeoff volume. This creates a delicate balance in the fuel-to-air ratio, which is simply the relationship between the fuel being burned and the air available to support and cool that combustion. If the high-pressure compressor spins too slowly, or if too much fuel is introduced, the engine suffers a hot start. Rather than a dramatic Hollywood fireball, a hot start is a rapid, quiet accumulation of heat that occurs because the core rotor speed is too low to force sufficient cooling air through the turbine section. To detect this trend, the flight crew closely monitors the exhaust gas temperature, or EGT. The turbine blades and guide vanes can tolerate extreme combustion heat only because high-pressure cooling air is channeled through microscopic passages in their surfaces, keeping the metal cooler than the surrounding gas. During startup, however, this protective boundary layer is barely established. If the gas temperature rises too high, the metal absorbs the heat directly. While exact limits vary, ranging from approximately 650 degrees Celsius in some specialized engine controllers to 725 degrees in standard flight manuals, any exceedance is dangerous. As the engine's operating instructions state, the exhaust gas temperature has a direct effect on the service life of engine hot section components. Even a brief over-temperature causes microscopic thermal fatigue, coating damage, or warping that quietly degrades the machinery and shortens its operating life. For this reason, pilots monitor the start as a trend reading team. Instead of watching a single limit, they continuously correlate the rising core RPM, the climbing EGT, the onset of fuel flow, the rise of oil pressure, and the total acceleration time. If these variables do not rise together in the expected sequence, the start must be aborted. When the fuel valve opens, the engine relies on immediate ignition to consume the incoming spray. If the igniters fail to spark or the electrical energy is too weak, the engine enters a state known as no light off. In the cockpit, the indicator of this failure is a complete lack of thermal response. While the N2 core spool continues to spin, the exhaust gas temperature remains flat. This silent gauge is deceptive. A flat temperature reading does not mean the combustion chamber is empty. Instead, aviation fuel continues to spray into the core, pooling in the combustor and draining into the exhaust path. In turbine aviation, this is a wet start, defined not by water, but by the rapid accumulation of raw, unburned fuel. If the igniters suddenly fire after this accumulation occurs, the pooled fuel ignites all at once. This delayed ignition triggers a sudden, violent expansion of gas, or a raw tailpipe fire streaming directly out of the exhaust nozzle. To prevent this, starting instructions mandate a strict 30-second window. If the temperature does not rise within 30 seconds of fuel introduction, the crew must cut the fuel, shut off the ignition, and use the starter to dry crank the engine, purging the raw fuel before it can ignite. To grasp the physical scale of this transition, it helps to examine a single, concrete example: the CFM 56-7B turbofan, the power plant driving the Boeing 737 NG. In the cockpit, pilots monitor the engine's rotational speed through two distinct indicators, N1 and N2. These are not simple tachometers displaying a single engine speed. Instead, they represent percentages of two entirely separate, independently rotating shafts. 100% N2, the high-pressure core spool, represents approximately 14,460 revolutions per minute. When the engine reaches a stable ground idle, this core rotor spins at roughly 62 to 66% N2, or about 8,400 revolutions per minute. Meanwhile, the low-pressure fan spool, N1, spins at its own lower speed reference, with idle values varying depending on the specific engine model and control schedule. The passage from a dead machine to a self-sustaining turbine takes only 30 to 35 seconds. In this half-minute window, the engine progresses through 3 rapid phases: motoring, light off, and acceleration to idle. During motoring, the friction-heated core registers an exhaust gas temperature of around 320 degrees Celsius. Within seconds of ignition, the EGT rises by roughly 200 degrees, reaching a normal startup peak near 530 degrees Celsius before settling back down to stabilize near 340 degrees at idle. The volume of air shifting during this transition is equally massive, though public engineering data reveals how easily units can be misconstrued. Some operational analyses cite core airflows of 50 pounds per second during motoring, 200 pounds at idle, and up to 900 pounds per second at takeoff. Yet official certification documents report a total engine mass flow of 350,000 pounds per hour at maximum thrust, which translates to a much lower real-world rate of under 100 pounds per second. This stark discrepancy reveals why engineers must verify units, station definitions, and source authority before treating any airflow metric as an absolute value. Regardless of the exact baseline, the core must quickly scale its breathing from a restricted starter-driven draft to a self-sustained gale. When fuel ignites inside the CFM56-7B, the N2 spool is expected to accelerate rapidly toward its self-sustaining ground idle speed of 62 to 66% N2. But in a simulator reconstruction of an abnormal start, a different pattern unfolds. Combustion begins, yet the core fails to accelerate normally. This is a hung start. The igniters spark, fuel burns, and the exhaust gas temperature rises. But N2 stops climbing or rises far too slowly, flattening out below the expected path while the start timer continues to tick. In a normal start, expanding gas acts in tandem with the pneumatic starter to drive the core upward. If the starter torque is weak, APU bleed air pressure is too low, or there is an unobserved compressor issue or fuel system restriction. The engine becomes trapped in an unstable state. It is burning fuel and producing high temperatures. But because the compressor is not spinning fast enough to draw in fresh air, the engine cannot generate the aerodynamic forces required to drive its own rotation. This is where the N2 acceleration slope, the rate of RPM increase per second, becomes the decisive trend. Pilots track the slope of the curve rather than focusing solely on the final RPM number. If that slope flattens, the start timer becomes a limiting boundary. During a typical start sequence, the flight crew expects the engine to reach starter cutoff, typically between 45 and 50% N2, within 30 seconds of fuel introduction. The starter cutoff is the essential milestone associated with stable core operation. If the engine remains hung below this threshold, it has lit without crossing into a stable operating condition. Under the Boeing 737 NG's checklists, this requires an immediate manual abort. The crew must move the start lever to cut off, cutting fuel and terminating the ignition. The peak of this event is the clinical interruption of the sequence, protecting turbine blades from structural damage caused by persistent heat and inadequate cooling airflow. Some operational notes describe cases where N2 stalls as high as 56% with a starter valve that fails to close, but certified procedures prioritize the absolute limits of time, temperature, and acceleration. This intervention prevents a mechanical failure from becoming a destructive thermal event, managing the transition from a static machine to a running engine through precise data trends. The physical transition of startup does not remain confined inside the metal cowlings. As the starter forces the core to rotate, the engine begins to violently redefine the physical space around the aircraft. Even during low-speed motoring, before ignition has occurred, the fan inlet acts as a high-volume vacuum. Ground crews must treat the area directly in front of the engine as an active hazard zone. At idle, this suction can draw loose tools, baggage equipment, and personnel toward the spinning fan. Standard procedures typically require a safety margin of at least 10 feet in front of the inlet, extending to 15 feet when ambient winds exceed 25 knots. Along the side of the cowling, a clearance of 5 feet protects ground crew from contact with the structure. But the threat behind the engine is even more expansive. The exhaust nozzle converts quiet air into a high-velocity, high-temperature jet blast. At idle, this thermal column can exceed 200 degrees Celsius, retaining enough kinetic force to move ground equipment or injure personnel over a distance of 200 feet. These clearances are not static rules. They scale with wind, aircraft type, and local operator procedures. Ground safety discipline represents the external counterpart to the internal engineering transition. Starting a jet engine is both a thermodynamic passage inside the core and a physical boundary line drawn on the concrete. Before the introduction of modern digital engine controllers, managing the transition of a starting jet turbine required constant, highly synchronized human intervention. On older aircraft like the Boeing 727, Douglas MD-80, and early versions of the Boeing 737NG, the flight crew manually directed every stage of the start sequence. The flight engineer and pilots closely monitored the rising core speed, manually introduced fuel by moving the start levers at a precise rotational threshold, tracked the exhaust gas temperature, and physically commanded the starter to disengage once the engine became self-sustaining. This manual coordination meant the crew had to recognize and react to changing thermal and aerodynamic conditions in real time, leaving little room for error if the engine began to trend toward a hot or hung start. On the modern Boeing 737NG, this dense workload has been consolidated into a single selection of the start switch. This automation is managed by the Full Authority Digital Engine Control, or FADEC. Rather than acting as a simple system override, FADEC has complete, independent authority over the engine's fuel scheduling, ignition timing, starter air valve operation, and temperature protection. By continuously processing data from a network of sensors, the computer calculates the exact relationship between rotor speed, internal pressures, temperature, and elapsed time to manage the startup sequence. Yet the introduction of digital automation does not mean the physical challenges of starting a jet engine have vanished. A failed pressure sensor, a sticking air valve, or a degraded pneumatic starter can still prevent the core from accelerating normally. For this reason, pilots do not simply turn the switch and look away. The flight crew remains responsible for supervising the start, acting as the final safety system to detect anomalies that may fall outside the computer's automatic abort parameters, such as abnormal oil pressure rise, starter malfunctions, or internal engine fires. If the start must be aborted, the system executes a highly coordinated shutdown sequence. The first priority is to cut the fuel flow and terminate ignition, arresting the rise of temperature before the structural limits of the turbine blades are breached. If the starter remains engaged, the engine continues to motor, drawing a continuous draft of cool air through the compressor and combustor. This process, known as a dry crank, serves to purge any unburned fuel vapor and lower the internal metal temperatures before another start attempt can be made. Every single startup sequence also functions as a highly detailed diagnostic test. The FADEC records and stores critical performance metrics from each event, including the exact start duration, the N2 acceleration slope, peak exhaust gas temperatures, oil pressure development, and vibration levels. Maintenance engineers analyze these records to detect subtle, progressive deterioration before it leads to an operational failure. In one documented case study, a commercial operator noticed a fleet-wide increase of approximately 2 seconds in average engine start times over several months. Rather than a sudden mechanical breakdown, trend analysis of the start data indicated a systemic drop in starter performance. Technicians traced the issue to a leaking bleed air valve in the pneumatic supply line, which was reducing the pressure delivered to the air turbine starter. Replacing the worn valve immediately restored the normal acceleration profile, demonstrating how small deviations in startup metrics can reveal hidden system wear. Gradual shifts in the N2 acceleration slope can similarly warn engineers of compressor fouling, turbine degradation, or pneumatic leaks long before the engine is dispatched for flight. Ultimately, starting a jet engine is a highly controlled, thoroughly monitored passage from a cold, static machine to a self-sustaining gas turbine. If you want to discover the hidden engineering behind the complex machines of our modern world, subscribe. Today, thousands of flights depart daily, each beginning with this silent, high-stakes transition. As propulsion technology pushes toward even higher temperatures and tighter tolerances, the margin of safety remains locked within these first critical seconds. This routine startup is actually a masterclass in automated vigilance. Ultimately, the greatest triumph of aviation engineering isn't just keeping a jet in the air, it is the precise, invisible choreography required to safely bring it to life.